Welcome to the atomic spectrum of hydrogen. Alright, so we've already talked about how electromagnetic radiation composes an entire spectrum of energies, frequencies, wavelengths. Now, a continuous spectrum is the spectrum of colors that's visible when white light is passed through a prism. So one way we can generate white light is by looking at the sun. Another way is by taking an electric arc across a sufficiently high voltage, and that will generate white light. So if we take that white light and we take just a sliver of it, pass that through a prism, the prism spreads out the various frequencies, the various wavelengths, spreads them out in space, and so we see the various colors. Now, with white light, we have other colors that our eyes can't see. We have the ultraviolet and the X-rays and gamma rays over this way. Now, of course, the X-rays and gamma rays with this sort of source, we won't have very many of those. And then we have the color spectrum, so red, orange, yellow, green, blue, indigo, violet, going up in energy. On the low energy side of the red, we have the infrared. Then we get to microwaves and radio waves below that. So those waves exist here, that radiation exists, our eyes just can't see it. So a continuous spectrum looks something like this. We see all of the colors of the rainbow, and the other colors or the other forms of light would exist outside of that. Now that's different, a continuous spectrum is different from a line spectrum. So a line spectrum is the spectrum of just a few sharply defined lines at specific frequencies. So if we take, say, a glass bulb and put hydrogen gas inside, and we make an electric arc discharge through that hydrogen, so that electric current has to flow through the hydrogen gas, we will excite the hydrogen atoms, and those hydrogen atoms will give off light. Now, the hydrogen atoms are going to give off light of a very specific, or at very specific frequencies, at very specific wavelengths. They won't give off light of all wavelengths. And so, what we'll end up seeing when we take that light, take just a narrow slit of that light, and pass that light through a prism, we don't see a continuous spectrum. We see a line spectrum. So we see just, in the case of hydrogen, just 4 lines, 4 wavelengths or 4 frequencies of light that we see from that hydrogen being emitted from that hydrogen gas. And so the line spectrum of each element is unique. Now, scientists a few hundred years ago were trying to explain why the line spectrum of each element was unique. Why were they not all the same? And furthermore, why were there lines? Why was it not a continuous spectrum? And that explanation furthers the model of the atom that they had developed. So, hydrogen has lines at 410 nanometers, which is violet, 434 nanometers, which is blue, 486, which is green, and 656, which is sort of an orangey yellow. So this is the 410, that's the 434, this is the 486, and this is the 656 nanometer light. And again, you can see that sort of spread out here. We only see those 4 colors. And in between, it's black because there is no light being emitted there. And so, why does hydrogen only emit light at these 4 wavelengths? Because remember that wavelength and frequency are tied, and those 2 are also tied to energy. So these 4 wavelengths, these 4 frequencies, mean that light is coming out of hydrogen at only 4 energies, or at least only 4 energies within the visible range that we can see. So that means certain things. So the light is coming out when electrons are giving off energy. Well, if electrons are giving off energy, and they have to be one of these four frequencies, one of these four energies, then the electrons have to be only able to give off certain amounts of energy, these amounts of energy, right? Or at least these amounts within the visible range, within the range that we can see. There may be other energies that are higher in energy than this, or lower in energy than this one, but we can't see them. So within the visible range, there are only four energies, which means that if those electrons can only give off energy of certain values, then they must be able to have energy of a certain value. They must not be able to have any energy that they wish. So, again, only photons with certain energies are allowed to be emitted from hydrogen. The electrons must only be allowed to have certain energy values within hydrogen, which means that they must be certain distances from the nucleus. Now this is because the electron and the proton, or the multiple protons in any atom other than hydrogen, any element other than hydrogen, that electron and proton are attracting each other. As the electron gets closer to the proton, it's losing energy. It's losing energy because it's falling down into the potential well of that attractive force attracting that electron to the proton. Because remember, the electron at infinite distance from the nucleus has an energy of 0. And as it gets closer to the nucleus, it's falling down. Just like a ball falling closer to the surface of the Earth. As the ball gets closer and closer to the Earth, as that ball gets closer to the Earth, it's losing energy. To go the other way, to raise the ball from the surface of the Earth, or to pull the electron away from the nucleus, we have to put in energy. We have to do some work to move that object farther away from the center that it's being attracted to. So when the electron gets closer to the nucleus, it's losing energy. Now, if the electrons can only have certain energy values, that means that the electrons can only be certain distances away. And there must be, most of the distances must not be allowed. The electron must only be able to have certain distances out from the nucleus. But this idea of only certain distances being allowed conflicts with Rutherford's atomic model. Furthermore, these distances from the nucleus vary with the element that you have, because within hydrogen we see some line spectrum. That means that the electron can have certain energies. But with a different element, like helium, well, now we see other energies. Other energies, we see other lines, which means other energies are allowed, but that means that these energies that are allowed for hydrogen are not allowed for helium, and vice versa. So, Rutherford's atomic model allows electrons to be anywhere outside the nucleus. Remember, Rutherford had the very, very tiny, very, very dense, positively charged core, the nucleus, right? That's where all the protons were. But outside of that, Rutherford doesn't really say anything about where the electrons are, except that they're outside the nucleus. So, in Rutherford's model, the electrons are allowed to be anywhere in this range, right? Anywhere in there. But if they can be anywhere in there, then they should be able to have any amount of energy. Which means when they change from one energy to another, they should be able to give off any amount of energy. But that can't be, because that's not what we see. So, Rutherford's model must be wrong. Which gets us to the next video in the sequence. So, that was the atomic spectrum of hydrogen.